What's going on, everybody? This is Mr. Diamond, and we are going to be doing Section 3 notes of Chapter 2 of Advanced Chemistry, Chemistries in Solutions, or Chemistry in Solutions, I guess is how I should say it, net ionic equations, solubility rules, and colligative properties. So we're going to start with colligative properties, and we just talked about molarity, molality, percent by mass, percent by volume, and all those concentrations. And I mentioned that molality, which was very dumb and sounds like molarity but is slightly different, is useful for like exactly one thing. So you may have been wondering, well, what is that one thing? And it turns out it's relevant when you're doing calculations involving colligative properties, which I assume brings up the question, okay, well, what is a colligative property? And the answer is that it's a property of a substance that does not depend on the type of substance dissolved, only the concentration of the solute. Or they don't care what they have in solution, they just care how much of it is inside, which is really weird because normally if you were like, oh, can I have a drink? And I was like, oh, well, there's stuff in solution. Your answer wouldn't be, well, how much? Your answer would be, well, what is it? Like, is it lead? Is it Kool-Aid? Is it sugar? Is it salt? What is it? You wouldn't go, I don't know. I think I'm only okay with it if it's like less than 20 grams of solute. Like, that seems really, really strange. But actually, there's a few common places where it kind of makes sense to think about it, where things don't really care about what they are, they just care about how much of it is inside of it. And those are boiling point elevations, freezing point depressions, vapor pressure lowering, and osmotic pressure. We're going to discuss each of these in a small amount, and there's going to be some calculations that accompany these first two and the last one. We're today going to be focusing on these first two here, though, the ones about boiling point and freezing point. So this is actually something we utilize pretty regularly in our day-to-day life, even if you don't really realize it. If you think about it, you can probably come up with ways that we try to change boiling points or freezing points. I just assumed there was going to be examples on the next slide. Well, the examples that I usually go back to are, number one, we put salt on the roads. And you may not realize that's exactly what we're doing, but when you put salt on the roads, you're actually making the freezing point of the water change. You're trying to lower the freezing point so it will get colder and it won't necessarily freeze and ice over. The most common example for adding something and trying to change the boiling point is actually salting your pasta water. When you boil pasta, you add salt to the water. More salt being added means a higher boiling point. That means the water gets hotter, and that means it cooks the pasta faster. Boiling point for a solution can be raised by adding solute particles, so you just need to add something to it. It's based on molality, a constant for that given substance, and then what's called the Van 't Hoff factor. We'll talk about that in a moment. We'll tell you how to get there. So the equation looks like this. Delta TB, which is change in the boiling point's temperature, is equal to the boiling point constant, which this is the one that I will make sure that I give you on the test. Any other one I will also give you. The molal boiling point constant for water is 0.51 degrees Celsius per molal, multiplied by the molality of solution times I, which is the Van 't Hoff factor. And then for freezing point depression, in this context, this is not what you are probably feeling as the climate dipped lower and you were stuck inside longer. This is the depression, meaning the same point as lowering. Boiling point gets elevated. You increase the boiling point, so it's boiling point elevation. Freezing point gets depressed. It lowers. It is reduced. So this is why we treat roads. We normally think about salt as like heating up the road, but like I mentioned a second ago, we actually put salt on the roads because we want to lower the freezing point of water. And that's actually also why salting roads only works to a certain point. If it gets cold enough, especially like the couple of weeks ago whenever we had that major snowstorm, we were out for a whole week, that was so cold for so long that the water was still going to freeze. Adding a whole lot of salt doesn't lower the freezing point that much. So when it's 0 Fahrenheit outside, it's still probably going to freeze. It can change based on molality, a constant that's different than the boiling point constant, and then the Van 't Hoff factor again. We will explain that in a moment. So change in freezing point is equal to Kf. This time it's the molal freezing point constant. It's negative here, but we'll talk about that in our example. Times the molality of the solution times the Van 't Hoff factor. Now, I've talked about that a whole bunch now. So what is the Van 't Hoff factor? It is a measure of the effect of a specific solute on the colligative properties of a solvent. It's determined by really just looking at the type of solute that you're using. If you're dissolving a single element, like calcium or lithium or manganese or nitrogen or something like that, just a single element, then it is 1. The Van 't Hoff factor is 1. If it is a molecular substance, then it is also 1 because molecular substances will not split apart. All we care about is how much stuff will be floating around in there. And if you drop in 10 solute particles that are molecules, molecular substances don't separate in water, so you'll just have 10 things floating around. But if you drop an ionic substance in, it's equal to how many particles the substance would dissociate into. So the best example would be like NaCl. NaCl is made out of sodium and chlorine. It's a ionic compound. So when you put it in water, it will actually separate into Na particles and Cl particles, meaning its Van 't Hoff factor is 2. For every 1 particle you put in, you will actually get 2 of them dissolved in the liquid. If you had something like aluminum bromide, AlBr3, that would separate into 1 aluminum, 3 bromines, so it would have a Van 't Hoff factor of 4. It would separate into 4 things for every 1 particle that you dissolved into it. So it's a little bit weird at first, just like a lot of our rules in this class, but after you get used to it, it goes pretty smoothly. You can identify them very quickly. All right, so I have a couple of examples here. We're going to check them out. We're going to determine the Van 't Hoff factor. We're going to do this one together right now. I just used NaCl. It's an ionic compound. It would separate into Na and Cl, so its Van 't Hoff factor is 1. The next one we have is C6H12O6. That is a covalent compound. Covalent compounds do not separate apart in liquids, so you would still just be left with C6H12O6, so its Van 't Hoff factor is 1. MnC2H3O2, or manganese 4 acetate. Manganese is a metal, which means this is an ionic compound. Polyatomics, remember though, don't normally separate apart unless I tell you otherwise. So this will actually separate into 1 manganese and 4 acetates, which would give us a Van 't Hoff factor of 5. O2 is a single element, so it would have a Van 't Hoff factor of 1. It won't split apart. And then CO2 is a molecular compound, which means it doesn't separate, which means it's going to have a Van 't Hoff factor of 1 as well. There we go. 2, 1, 5, 1, 1. Okay, these other examples, though, we are going to work in our separate video that'll be down there below. I'm going to work these out with you together. In the meantime, though, if you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.